So multi-dimensional digital signals look like this. So this is a nice image of a monarch butterfly, okay, in color. So this is a 2D digital signals, and if I zoom into that small little areas, okay, so this is by the wing, okay, so you catch the edge of the wing, and then the yellow of the butterfly, and then the pink purple color of the orchid, okay. So each of these little guys is called a pixel or a pair, okay. Now these can be depending on the value you assign, okay. They can be very black, okay. So if you assign this pixels to have value 0, it is that black, okay, as black as your display can support, okay. And then if you pick 128, for example, it will be gray, okay, some degree of gray. And if you pick 255, which is so this is an 8-bit example, okay. So we can go from 0 to 255, okay. Then it can be as white as your display will be able to show, okay. So now, but this is in black and white, okay. How do we represent color? Okay. Remember when we were young, we played these games, right? You mix different colors and you come up with interesting one, right? So the three main color is called R, G, and B. So red, green, and blue. With red, green, and blue, with certain percentage of red, green, and blue, you'll be able to generate a whole range of color components, okay? So for example, if you mix an equal amount of red, green, and blue, you actually get grayscale, okay? But if you only mix red and blue, you get magenta, which is rough, it's like purple in color. Or if you want to get yellow, then you just mix red and green, okay? So the way that the digital display works is that they're using the same fundamental frameworks, okay? So you have three color components, and you assign values to each of the components. These values, determine how much red, how much green, how much blue you have, and that come up with a color 2D signal like this. Now video sequences are just a very simple generalizations of 2D, right? Instead of having one still image like this, you have multiple still images captured very close to each other. So we're talking about 24 frames per second. In 1 second, you have 24 of these passing through your eyes, okay? And since it's coming through so fast, your brain automatically interpolates, okay? And you see a smooth moving images, okay? If you reduce the video rate down to maybe 3-4 frames per second, it's going to look very junky, right? I don't know if you have experience with video phone. That's bad quality video phone, okay? Okay, you might wave your hands, and then your mommy will totally miss it. She will not even see that you are waving, okay? Because it's not sampling fast enough, okay? But if you have 24 frames, 30 frames, then everything becomes continuous and smooth, okay? But that is also a challenge, right? We somehow have to keep up to that rate. We have to keep up to that rate. If we're not doing, if our design system, now today, to give you an examples, we'll take a look into some of the color spaces that we use, okay? RGB is just one way. But there's a lot of correlation between the R component, the G component, and the B component. So people think of a way to take away some of the correlation between the three color components and maybe represent things in a different color space. So one of the different color space is called YCRCB. So Y stands for luminance or the grayscale component. The nice things about this color space is that if you have a black and white television, then you simply throw away these two components, the color component. You just display that, and automatically. you get black and white TV. Okay, but if your TV actually has color capability, then you add the CR and the CB space, and then you get back your color. Okay, so YCRCB, also known as YPRPB, is used in component video. Now, when you go home tonight, and I want you to take a look at your DVD players in the back. Okay, the high-end DVD player will have component out. Component out. Okay, so it has the three colors component going out. Okay. And it will be labeled probably YPRPB. Okay, so that's what it is. This is simply a linear transformation. Okay, so R, G, and B are pixel values in red, in green, in blue. Okay, what you do is put it through the simple matrix. Okay, add some offset to it. Okay, and then you'll have Y, the component Y, CR, and CB coming in. Okay, now. Today, when we play around with it in MATLAB, you will see that most of the signal energy actually is in Y. Okay, Y contains, because it's the grayscale component, right? It contains most of the information that you need to see. The CR and CB only takes care of the color. Okay, so it has a lot less energy. Now, we talked about sampling before, right? Okay, we can do sampling without losing signal components based on the maximum bandwidth, right? Based on the maximum frequency. Okay, so if your CR and CB do not have much information, meaning that they do not vary a lot, you know, the maximum frequency is not high, then certainly you can do things like this, right? You can do downsample and lose very little, or if at all. Okay, so that's why sometimes, actually a lot of time in practice, people actually downsample the CR and the CB component. So every 4 luminance pixel, you're going to have 1 chrominance pixel, 1 CR pixel, and 1 CB pixel. Okay, so a total of 6. The group has 6, 4 Y guys. Okay, 1 CR, 1 CB. Okay, and today in MATLAB we're going to play around with this video sequence. Okay. And you will be able to verify for yourself that it actually works, and you can actually see the video. You can see how does the luminance space look like, how does the chrominance space look like. Okay. Now, to give you a little peek into, okay, so this is what the MATLAB exercise will do. Okay, we'll take a color video, for example, right, and you'll be able to extract. This is how the luminance or Y look like. Okay, as you can see, this is just a black and white version of that color image. Everything is here. Okay, you can certainly recognize the person and everything. And look how low frequency these guys are. These are the color components. Okay, it doesn't have strong edges, right? It doesn't have a lot of variation, a lot of texture. It seems to be very smooth. So these are the color components. Now this comes from a different color space. This is the YUV color space, which is another way, another linear transformation that people use to map RGB into YUV. Okay, so this is color, this is luminance, black and white, and this is the color, U and V for color. This is typically used in broadcasting, okay, in digital video. When people broadcast video over, say wireless communication channels, people use YUV. Okay, so this is now basic. So let's just take the matrix the way it is, and if you want to read more about it, you can do a quick Google on YUV, right? And then you can read all about how do people come up with these numbers. Okay, there's actually a reason why. Okay.